working principle of three-phase transformer and single-phase transformer being similar, it is expected that the constructional features of the two transformers will also be similar. However, in appearance the three-phase transformer looks significantly different. One is shown in this diagram. From outside it looks like a box or a tank fitted with a large number of accessories. In this lecture we will see how the main parts of the transformers are constructed, their purpose, and as well as the construction and purpose of these accessories. So, if we look at a cutout view of a transformer, we find that inside the tank we find the core of the transformer, the windings, the terminals, and there is a overhead conservator like this. The essential part of the transformer consists of a core with windings on the limbs. In the last lecture we have seen that a three-phase transformer built as a single unit can be made up of three limbs. The returned limb for the flux is not necessary, since the sum of the fluxes are 0. However, this three limb construction does offer slight imbalance to the flux path. Therefore, for very large transformer a 5 limb construction is used, where the windings are placed on the inner limbs, the two outer limbs do not carry any winding. This provides a more balanced magnetic path for the three phase flux, and the windings, the phases operate more or less independent of each other under balanced operating condition. There is another construction. Incidentally, this construction and the next, these are called court type transformer. There is a different construction which is called the shell type transformer, in which case the three phases operate on completely separate magnetic circuit and they operate independently one of each other. However, for most three phase power transformer, the three limb construction is the most common, and that is what we will assume in our discussion. So, here is a look at the assembled three limb core. There are several parts to it. These vertical parts are called the core, the horizontal one is called the yoke. As in the case of a single phase transformer, these are not solid iron bars. However, they are made up of thin steel lamination. The purpose of the core is similar to that of a single phase transformer, that is to provide low reluctance path for the flux and as well as to support the winding and provide mechanical strength. Since the flux flows along this direction, the transformers cores are laminated along this in this way. So, these are made up, these cores are made up of long strips of thin steel plate, the material being either hot rolled or cold rolled grain oriented steel. For large transformer, it is usually cold rolled. Since these are made up of steel laminations, it is necessary to bolt them down with clamps. These are the clamping pieces of the core. if I look a top view of one of the core along with the winding, it will look somewhat like this. This part is the actual core cross section on which there is a insulating bobbin cylinder, this being made up of pressboard or SRPB cylinder. On the cylinder, first the LV winding will be placed, then there will be a gap between the LV winding and the HV winding. There will be a second cylinder on which the HV winding will be placed, and there will be a gap between HV and LV winding through which cooling fluid may be circulated. One interesting thing about the core structure is that it is not square. The reason is simple. In order to support certain amount of voltage and not to exceed a given flux density, the core cross section must have some minimum area, and it is well known that for a given area a circle has the minimum circumference. Since the windings are placed around the core, it is necessary, it is advantageous that this circumference is minimized, so that the length of the mean turn of both LV and HV winding can be minimized, thereby minimizing the resistance and the losses. Therefore, it is necessary to accommodate the core of a given area with minimum circumference. Now, ideally the core cross section should have been a circle, but cores also needs to be laminated. If a very good approximation to this circle is made, then laminations of differing continuously varying width will be necessary, which is problematic from the point of view of production. Therefore, a compromise is arrived at. Therefore, generally instead the cores are made the step form. This is called a cruciform core with only 2 steps. For larger transformer, even larger number of step 5, 6 up to 6 is used, so that the circular space in this is more maximally utilized. The next important thing in transformer construction are the windings. The purpose of the windings are to carry the magnetization current that produces flux and also transfer power from one winding to another. These windings are made up of solid or stranded copper or aluminum strips. There are different types of windings that are used. It depends on the power and the voltage rating of a particular winding. This figure shows some of the common winding configurations. The first one is cylindrical, then second one is called the helix, and the third one is called the crossover. These are normally used for low voltage winding. This is for high voltage winding with many turns. Here we have a few more. This is the same helix. This is called a disc helix. This is the disc where the windings are wound in a concentric manner to form a winding disc. This is the crossover. This is the multi-layer helix. The same helix can be put on several layers of them to form this multi-layer helix. Now, depending on the application, MVA rating and the KVA rating of the transformer in question, different windings are used. For example, if it is a distribution transformer, MVA rating, let us say up to 1 MVA, the HV voltage rating is 11 kV to 33 kV. Then the HV winding will be normally it will be either crossover, this is the crossover winding, or this is the crossover winding, or multi-layer helix. Similarly, the LV winding for distribution transformer will usually be rated at 440 volt. The choice of winding for this is helix, which is shown here. This is the helix winding. This is on the lower spectrum. Let us see something at the medium spectrum, which is the subtransmission level. This is, let us say, from 1 to 30 MVA. The HV voltage will be in the range of 33 to 66 kV. The preferred HV winding type for this is disc. This is the disc winding. The LV voltage for this type of transformer will usually be 11 kV, and for this LV winding usually disc or helix winding will be used. This is the disc winding and this is the helix winding. Coming back, going further higher up in the MVA rating, transmission. It will be 30 MVA and upwards to higher. The HV voltage will be in the range of 132 kV to 400 kV. The preferred choice is disc or multi-layer. The LV voltage can be 11 kV, 33 kV or 66 kV. This is disc or disc helix. This is the multi-layer helix, this is the disc and this is the disc helix. Coming to generator transformer. This is also 30 MVA or upwards. The HV side is again 132 kV to 400 kV, and the choice is disc or multi-layer. LV voltage is the voltage generated by the generator will be in the range of 11 to 22 kV, and the choice of winding is disc helix. So, this is a rule of thumb, but depending on the special application a particular type of winding is chosen. Whatever may be the choice of the winding, it must be ensured that there is enough space around the conductors, around different layers of conductors and between different levels, so that the cooling fluid, usually oil or air, can flow through it. So, this is the inner cylinder. You must have some gap before the winding starts. These are usually provided by spacers, which are non-conducting material, and spacers are placed here also, so that there are ducts formed in between the windings, between winding and the inner cylinder, between winding and the outer cylinder and the layers of the windings. This is necessary in order for the cooling medium, that is the cooling oil, to flow in an uninterrupted manner, so that it can carry the heat generated by the I square R loss in the windings to the outside cooling medium. Another interesting feature of a 3-phase transformer, which is normally not found on single phase transformer, is the arrangement of tapping. Tapping is necessary so that the voltage on the HV or LV side can be controlled. The tapping is done by either inserting additional turns in a particular winding or removing some turns from a winding. Therefore, there will be a section of the winding, usually on the high voltage side, which will have several terminals coming out from them. Here these terminals are in this picture on the 3 phases, these terminals are shown, and there will be a selection switch which can choose the terminal at which the transformer external connection is connected at any point. There are two different ways this tap changing can be done. One is called the offload tap changing, where during changing from one tap to another, there will be a momentary disconnection of supply, and onload tap changing, where the supply will not be disturbed. The next figure shows how a online tap changing can be arranged. So, this is, let us say, a particular winding of the transformer with 5 tap positions. We want to go, let us say, from once the connection was at tap 2, we want to go to tap 3. For onload tap changing, it has to follow certain sequence. This is the selection switch. So, first the selection switch, which was at position 1 and this position, each of these taps are connected with a current limiting resistance. While it is supplying from tap 2, it is the position of the switch is this. This resistance is shunted by this short circuit. So, current actually flows through this path and not through this resistance. The first step in tap changing is to move this switch from this position to this, so that this external connection is now removed from tap 2, still connected to tap 2, but now through this resistance R A. Next, we move to the position where these two resistances are shorted by this diverter switch. This is the reason why these resistances are necessary, because without these resistances, if we move this diverter switch, then there will be a short circuit between these two taps and there will be large circulating current which may damage the part of this winding. So, these current limiting resistances are necessary. So, now current is flowing, half of the load current is flowing from here, half of the load current is flowing from here, and there is a circulating current small I. Next, we move to this position where tap 2 is completely disconnected and tap 3 is connected through the current limiting resistance RB, and finally, we move here where this RB is shorted by the diverter switch. So, this is the sequence of operation by which one can do online or on load tap changing, that is without disconnecting the transformer from the load. We have mentioned in one of these slides that it is necessary to circulate cooling fluid through the windings and the core of the transformer in order to prevent the temperature of the transformer rising to a very high level. Now, there are different methods of cooling. For small transformer dry type, it is usually not necessary to use any separate cooling medium. The transformer is left outside, the ambient air is sufficient to cool the transformer. This is called air natural cooling. Or AN. On a slightly higher rated transformer, natural air circulation may not be sufficient to prevent temperature rise of the transformer, in which case the transformer may be cooled using a fan. This is called air blast cooling. Except for in very special applications where using a cooling medium is hazardous, these are used only for small rated transformer. For a large majority of transformers, they are usually oil immersed and the transformer oil works as a medium of cooling. This figure shows such an arrangement. These are the transformer core and winding. This is placed inside a steel tank and the tank is filled with transformer oil. The reason for using oil is that it is a better conductor of heat than air and it has a higher coefficient of volume expansion with temperature. Therefore, sufficient circulation is easily obtained on account of natural thermal head that occurs in the transformer because of heat produced by different mechanisms of loss such as the core loss and the copper loss. So, the natural cooling by oil works this way. As the oil heats up, becomes lighter, moves upward and comes in contact with the transformer tank wall, through which coming to the transformer wall, this heat is dissipated to the ambient. This is called oil natural cooling. Now, for smaller rated transformers, a simple transformer tank is sufficient to provide this cooling. However, for larger transformer, the surface area provided by the tank alone is not sufficient and therefore, the tank's area is usually supplemented by a large number of either the tank surface is corrugated to increase its surface area. More commonly, circular or elliptical tubes are placed on the transformer tank, all around the transformer tank, in order to increase the cooling area. This is called, these are several categories. This is called oil, natural, air, natural, because neither the oil or not the air is forced through any pump or any other device. However, for larger transformer, natural cooling by air is not sufficient, in which case it becomes necessary to blow air to cool the heated oil. For this, normally the hot transformer oil is carried to an external heat exchanger through piping arrangement, and the heat exchanger is where the heat is transferred from the oil to surrounding air, and it is usually cooled using a fan. This method is called oil natural air forced. This heat exchanger can also be cooled by forcing water circulate around the oil carrying pipes, then it will be called oil natural water forced. This is used normally in hydroelectric generating stations for the generator transformer, because a large quantity of water at a sufficient head is available, and water is a better medium of cooling than air. For even larger transformer, the normal thermal head of a transformer is not sufficient to provide enough cooling of the transformer. Therefore, the oil is circulated through the transformer by using a oil pump. The rest can be similar to oil natural air forced. So, this oil pump circulates the cooling oil through the transformer at a given flow rate in order to remove the heat generated from the transformer faster. So, this is called oil forced cooling method. Oil forced cooling method is usually used with a heat exchanger which is cooled by fan. So, this will be complete scheme will be known as oil forced air forced. Such a scheme is shown in this diagram. It is interesting to note that this scheme can operate in variable mode. For example, the oil pump and the fan need not be on all the time. If the transformer is lightly loaded and dissipating less heat, then both the oil pump and the fan may be turned off, and the scheme can work in a oil natural air natural cooling method. If the load increases to some more extent, then maybe the fan will be turned on first, so that it will work as a oil natural air forced method. It is only at near about rated load or at rated load that it will work as a oil forced air forced cooling method. This way the power consumption for cooling will come down and the efficiency of the overall efficiency of the transformer will increase. The next important constructional feature of a transformer are its bushings. These are the bushings. These bushings are meant for making connection to the transformer from overhead lines. It has to be ensured that this transformer tank is normally earthed. So, when you are making high voltage connection through the tank to the transformer winding, it has to be ensured that there is no flashing or short circuit or otherwise degradation of the insulation between the high voltage terminal and the earth transformer tank. This is done through special bushing. This figure shows the construction of one type of bushing called the oil filled bushing. There are two types, the oil filled type or the capacitor type. This is for a outdoor transformer. The bushing in its simplest form is a housing, insulated housing, mostly of porcelain, with a hollow space in between through which the connecting wire or the rod can be placed. So, this is the bushing. These are the porcelain discs which provides the insulation. So, from the top to the bottom, here is the entry of the cable and this is the conductor. These are normally oil filled with a expansion chamber on the top and also provided with arcing horns, so that if there is a flashover, it occurs between these arcing horns. It is also provided with a current transformer which measures the current flowing through the terminal. These protrusions of the porcelain cylinders provide for extended insulation and prevents against corona. This tank is normally oil filled. This provides a space for expansion of the oil, so that with variation of temperature, and this normally is insulated with SRPB paper. So, this is the construction of oil filled bushing. There is another type of bushing construction which is called the capacitor type, in which alternate layers of metallic conductor and insulating material are wound in a cylindrical fashion to form a series of capacitor between the inside conductor, high voltage conductor, and the outside plane, which is normally earth. So, the potential distribution in the radial potential distribution along the radial direction of the bushing is equally divided. For 3-phase transformer, there will be 3 such bushings, and the first figure, these are the bushings. For external the transformer that are used for outdoor operation, there will be this porcelain petticoats which prevents again rain and dirt pollution. For internal or indoor transformer, these porcelain cylinders are smooth. The transformers are to be also provided with sufficient protections. The protections, electrical protections, are normally provided by relays. Here is one arrangement that provides protection against transformer overcurrent or short circuit. This is provided by what is called the Buchholz relay. This figure shows the construction of a Buchholz relay. This usually consists of a chamber which is normally filled with oil, and it consists of 2 trip floats which holds 2 contactors. In the normal situation, this chamber will be filled with oil, and both the floats contacts will be open. However, if there is some short circuit, some fault, so that there is overcurrent in the transformer, gases will be generated because of heating of the transformer oil, and since this is filled with oil, the gas will move up and will push the oil level down. As a result, this is hinged, so this will turn around, the first float will turn at the top float will turn around and will possibly close a contact here. So, which will sound a alarm and tell the operator that something is wrong. However, a normal overcurrent or overcurrent for small duration will not produce enough gas to make the bottom float operate. This will happen only if there is a severe or a direct short circuit and violent gas generation, then the level will go down further and even the contact of the bottom float will be closed. This float is connected to a trip circuit which will close the tripping circuit of a circuit breaker and the transformer will be disconnected. So, this Buchholz relay is used with many large size 3-phase transformers. So, here we can see the final assembly of a 3-phase transformer. The different parts are, this is the transformer tank which is visible from outside, these are the cooling pipes, these are the cooling pipes. Inside this tank, this is the oil level, this is the actual core and winding configuration. So, this is the top core clamp, this is the LV winding, this is the HV winding, between HV and LV there are oil ducts, this is the LV insulating cylinder here, this is the HV insulating cylinder here, the bottom core clamp, and these are the tappings, these are different insulating material. Now, this does not show a bushing because the cables, underground cables may be connected through this cable box, and this also has porcelain insulating terminal, but does not show a bushing, and there is a provision for seeing where the tap position is, and this is the tap switch. This is one view of the transformer. The second view is this is the front view. This mostly shows the other auxiliary connection, for example, the cover, the lift lug, there is a air vent or breather. Note that there is a conservator on the top of the tank. This conservator is normally, the tank will be completely filled with transformer oil. In fact, the transformer oil will also fill the Buchholz relay, will possibly end somewhere here. The reason why it is done is that, so that the minimum of the transformer oil surface comes in contact with air and it does not absorb moisture from the air. The conservator provides a space for expansion of the oil. As the transformer heats up, the oil expands and flows through the tube to the conservator. Now, this conservator, although it is not shown here, is connected to the external atmosphere through what is called a breather. So, this is the conservator. Conservator will normally have a pipe extending down, this is called the breather, and the breather end there will be a cylinder like this. This cylinder will contain silica gel, so that the air that comes in or out of the converter is always through this silica gel, which absorbs moisture. So, the contamination of the transformer oil due to atmospheric moisture in the atmospheric air is minimized. So, this is the breather, this is the cold oil level here, it is above the transformer, that the cooling tubes, this is again the tapping switches here, this is the steel tank, this is the core clamps, these are the insulated bolts, and this is the earthing socket. See, the transformer oil needs to be periodically changed. So, there is a oil drain valve, these are the coils, you can place a oil gauge here, and there is a provision for inserting a thermometer, so that you can measure the temperature rise of the oil from outside. So, this more or less summarizes the main constructional features of a 3-phase transformer, the main parts of which we can summarize as follows. The transformer, the main parts of the transformers are: one is core. The purpose of this core is to provide low reluctance flux path, also provides support for winding. So, these are the purpose, this is the structural element. This is the purpose. This also provide support to the winding. As well as provides structural or mechanical strength. It should be realized that the transformer windings are subjected to substantial mechanical forces, particularly during abnormal operating conditions such as faults, and they should be designed to withstand such mechanical forces. The material for the core are silicon steel, normally cold rolled grain oriented CRGO. It is oriented in the direction in which the flux is expected to flow, and there are different types. For example, it can be coat type, which can again be either 3 limb or 5 limb, or it can be shell type. So, this is the types of cores. The next important feature is the winding. Important construction feature is winding. The purpose of this is flux protection and power transfer between input and output. The material used are either solid or stranded copper or aluminum conductors, maybe solid stranded conductors or strips. There are different types of winding. HV winding can be of crossover, disc, multilayer, LV winding can be of helix, disc or disc helix. Third important constructional element are the insulators. Provide electrical isolation between different parts. The material used are pressboard cylinders, SRPB cylinders. SRPB stand for synthetic resin. Paper and transformer oil. There are two types of insulators. One is called the major. This is between different windings, core and winding, and between phases, and minor, which is between different parts of the same winding, and the third type is the oil barrier, which is the insulation relative to the tank. The next important structural element is the bushing. The purpose is to provide external electrical connection. The materials are porcelain cylinders, conducting rods, insulating spacers, oil. These are two types, oil filled type and capacitor type. Then you have cooling arrangement. To restrict temperature rise. The medium of cooling are the material or components required for cooling are tank, oil, pipes, fins, heat exchangers, fans, oil pumps. These are the components required for the cooling arrangement, and you have different types of cooling. For example, air natural, air blast, oil natural, air natural, oil natural, air forced, oil forced, air forced, oil natural, water forced, oil forced, water forced. These are different types of cooling. They are used with increasing rating of the transformer. This is for the lowest rating, this is for the highest rating transformer. Then protection arrangement. To protect against faults. And you have all kinds of arrangement for this. The conservator prevents explosion, breather, explosion vent, then temperature in Buchholz relay, temperature indicator, etc. And then lastly the tap changer. So, this is to adjust to control voltage. So, you have to have additional turns, current limiting resistance RA, RB, diverter switch. This again can be of two types, one is on load and off load tap changers. So, this in nutshell summarizes the basic constructional features and their purpose and types of 3-phase transformers.